Alright, this circuit is drawn in a very obvious way, and we can see how the resistors are connected. So resistors 3 ohm and 1 ohm, these two are connected uh, in series with each other, and together these 3 ohm and 1 ohm, they are connected in parallel with a 2 ohm, and this whole big parallel branch is connected in series with a resistor R. So in part A and part B, you are to calculate the voltage across the 3 ohm resistor and the 1 ohm resistor. You are given I1 to be 0.50 amperes. So it's a simple application of Ohm's law. On the 3 ohm resistor, apply Ohm's law. Current is given to be 0.5 amperes and the resistance is 3. So that gets you 1.5 volts. Do the same thing for the 1 ohm resistor, apply Ohm's law to get the answer 0.50 volts. So now you can see that the voltage across the 3 ohm resistor is 1.5 volts and the voltage across the 1 ohm resistor is 0.5 volts. You can add these two voltages up to get you the voltage across this path, this parallel path. Okay. Now moving on in part C, you are to calculate the voltage across the 2 ohm resistor. Notice just now in part A and part B, we could have added up the two voltages on the top path, and that voltage that is added up will be the answer to part C, because these are two parallel paths, and as we all know, parallel paths always have the same voltages across them. So that's how we can get the answer to part C. Okay, so add up the two values just now and you get 2 volts across the 3 ohm and 1 ohm resistor, and also across the 2 ohm resistor. Now in part D, you are to calculate the current through this 2 ohm resistor, and after that calculate the total current of the whole circuit I. So not difficult at this stage, because you know the resistance of this 2 ohm resistor is 2 ohm, and you know the voltage of this 2 ohm resistor to be 2 volts. So you can just apply Ohm's law to calculate what is the current that passes through the 2 ohm resistor. And the total current is simply just the sum of I1 and the answer that you got here. Because in a parallel branch, the current that flows into a junction will flow out and the values must be consistent. So adding up the two currents, you get a total current of 1.5 amperes. Now in part E, you are to calculate the voltage across resistor R, and in part F, the resistance value of this resistor R. And finally add up all the resistance together to get the effective resistance. So we know from just now that the voltage across the whole parallel branch here is 2 volts, and these 2 volts must be summed with the voltage across R to get us 6 volts. Therefore, we can use this voltage equation for series circuit to get our answer to part E, that the voltage across our resistor R is 4 volts. So 4 volts plus 2 volts gets us 6 volts EMF value. In part F, since now we have figured out the voltage of resistor R, and we do know the current of the whole circuit from a previous part, we can apply Ohm's law again to find out what is the resistance of the resistor R, which is 2.7 ohm. And lastly, the effective resistance, we could have slowly added up all the resistances, and we can get the answer, but there's actually a faster way. Since now we know the total voltage, which is the EMF 6 volts, and now we know the total current, which is over here 1.5 amperes as found in the previous part, we can just apply Ohm's law on the whole circuit to get us the resistance of the whole circuit. That's the answer. Therefore, the answer is 4 ohm.